Sup guys, welcome to today's show. So today we're going to continue our HTML project, and in the last episode we finished our lexer, which means we are now able to turn our HTML code into tokens. So the next logical step is to write the parser. And the parser in this case will simply be something that goes through a list of tokens and creates a stack. So basically, let's say we have this code. Seems to be lagging a little bit. It's difficult to write. And then we have a text token. Let's say hello world. Then we close it up. So this will be transformed into the specific tokens. Tag start, text token, tag end. And that we know all about already. But when we parse these tokens, I want to create a stack-like structure, but not entirely so, because a stack has two operations, push and pop. When we push something to the stack, we put it like this. So we push the first token, then we push the second, and the third. And then usually we might pop something. And then the last thing that we put onto the stack will be the first to go, like this, and then this, and then this. So that is how a regular stack works, like the memory of a function, let's say. But I wanted to do it slightly differently, because we could do it like that, but then we would run into trouble if we, for example, wanted to create an HTML, which, let's say we have a B tag, and the logical thing would be to close that B tag here. But let's say that we, for some reason, closes it after the body. This is valid HTML, but the stack wouldn't be able to handle this, right? Because when we get here and we pop the last thing, it will pop off this one instead of the body. So we will have a special kind of pop. Let's call it a pop for alternative pop. And it will take an argument, which is a token. And this will pop off the last token of that kind. So let's say we have this stack body. We can have the B as well. And then the text token. And then we do an apop body, because that is what the code says, right? And then we will search to the stack in this order until we find the body, and we remove that. And we might have like 2 Bs or something, which also is valid HTML. And let's say we come down here. That means we want to pop off this one. And when we come here, we want to pop off this. So these are the 2 operations, push and apop. And when we encounter a text token, so let's remove this from the stack, and we will not put text tokens on the stack, by the way, and I'm going to tell you why. So let's clean up this code a little bit. Let's remove these B's. So this is, by the way, let's put it back. It's a better example than doing something with the HTML of their body, because they don't really do anything, right? So our stack looks like this when we encounter the text token. And every HTML tag will link to a function. So let's say this HTML has an HTML function. Body has a body function. And B has a B function. So when we encounter a text token, we look at the stack and we run the B function on the text token. And then we run the body function on the text token and the HTML on the text token. So we will run every tag function on that text token if it's on the stack. So let's say we have a foo bar down here. So we'll run all these 3 on the hello world text token. Then we come to this B. So then we'll do an apop operation on the B. And when we hit the foo bar, we will only run the body and the HTML on foo bar. And then these 2 closes, and we apop them. So in that way, we will be able to affect the text tokens based on what's on the stack. Simple enough, no? I think this is a rather elegant solution. Okie dokes. So let's run a parser, shall we? Let's write a parser. And I think we deserve a new file or 2, perhaps. So let's create a parser.c. And a parser.h. And let's also modify our makefile accordingly. So we'll have a parser O depending on parser.c and parser.h, which will run cc with the flags on the input file. And then we link with the parser. When we have this nice looking structure in the makefile, it's very simple and easy to add new files. So let's double check that we have the new files. Parser, yes we do. And if we try to compile with these new additions, it works. All right, so what shall these files contain? Well, before I forget, let's also include the parser here. And I don't really like these what's it called? Quotes. I think it looks a little bit more serious when we have it like this, right? So let's do that. And let's see the other files as well. This looks okay. This too. Here I want to change these. And let's add the pragma. Let's also modify this one. And for you beginners out there, the difference between having these brackets around the header file and having the quotes is that the quotes, then we are looking for files inside of the current folder. And when we have brackets like these, we usually look at the operating system's default include directory, where all the standard C libraries and stuff is located, the library header files. On my system, it's inside user include, but that depends. However, we can add our own directory in addition to the default one. So we just do dash big L, and then we put the directory, and we can put a dot for the current directory, which means that this should compile now. It does not. Sorry. Big L is for the library files. This should be big I for include files. Now it works. Nice. It's starting to be quite a big project, this. Alright, so let's write a parser, shall we? Right after this. Did you learn anything useful today? And do you want to support this channel? Go to drbirch.com/support. You can also click the button Become a Member. Thank you for your support. Alright guys, welcome back. So let's start writing our parser. And as usual, I will begin by defining the types. So let's start with the stack structure. So we'll define a, first, what should we call it? Tag stack, perhaps. Or no, let's just call it a stack. So we will have an S stack. And what shall it contain? Well, we need to make it a linked list. Or we don't necessarily need to, but I think I'm going to. It gives us the most flexibility. And this will be a list of tokens. But each stack structure will only contain one token. So we will have a token shall we make it a pointer? Yeah, I think we are going to, for now at least. I can't really decide. Let's not make it a pointer. So we'll have a token, and we will have a struct s stack next. And I think we will make it a dual directional stack. Dual directional linked list, I mean. So we'll have a next, but we will also have a previous. So we can go both up and down our list. And I think this will be all we need for now, at least. Maybe we should put the function here for convenience. So let's say we have a type definition for a function. And it will return one of our string structures. Like this, I guess. And the arguments, I'm not really sure what that's gonna be. We will probably have a token at least. Let's just say we have a token. It will probably be more things later on, but we just need a placeholder for now. Let's also include hyper.h. Let's say we have a function fun. And we type def struct s stack, and this will be a stack with a capital S. Alright, and we will have a constructor. So it will return stack pointer, make stack, will we create it empty to begin with? Yes. And then we will have the two operations. So we will have a push. Push operation, which will take a stack, and it will take a token, and it will return the new updated stack. So we also need to give it the garbage collector so we don't leak memory. And our apop will also have a garbage collector, a stack, and a token type is probably enough. I think. Well, let's start there. So we need to have this constructor, make stack, no arguments. Why is this erroring. Because it can't find this. It doesn't understand the make file. Maybe we can do this while we're developing. Just for convenience. I will change that back later on. Right, so we'll have a stack P. And we want a size. Size is equal to the size of a struct as stack. And then we malloc. Let's assert that we have a P, and then we zero the P. With the size. And we return it. Simple enough. Let's also be a little bit explicit. Or never mind. So the next operation is the push. And before we can write that function, we need another function. We need to find the last entry in the linked list. So let's call this find last. It takes a stack. Find last, we have a stack S. And we need a pointer. So we set P equal to the first in the list. And as long as there is a P next, we want loop. And P will be equal to P next at each iteration. Then we should just be able to return P. Yeah. And if we don't have an S, we'll return 0. By the way, let's not dereference this. Alright, so now we should be able to write our push, which takes garbage and garbage G. It takes a stack S and let's see the order, and then the token T. Alright, let's also include tokens.h. And let's assert that we have a G, or not a G necessarily. Let's assert that we have an S at least, and that we have a T type. And we need to have a pointer as well. Two, actually. We need to have a pointer for the last entry. And this push operation we will handle differently depending on, let's see, if the stack is empty, well, we can do something like this. If we don't have an S next, that means no, it does not. Because S next is 0 if we have an empty stack, but also if we have a stack of length 1. So how do we differentiate? Let's say if this function is empty, then it's a first. So then we have an empty stack. Maybe we should create an alias for that, just to be more precise. So let's define empty x so x fun is equal to, now we can do this, so if the function of x is 0, then we have an empty stack. So if empty s last is equal to s, otherwise last is equal to find last of s. And we want to allocate maybe we should create this in the functional style, like we have done this far. So we create a new list each time. Which means that we will have an s prime instead. And if s is empty, last will be s. No, s prime will be make stack. So create a new empty stack. And last will be equal to that. And if it's not empty, s will be equal to stack copy s, g and s. And last will be equal to find last of s prime. So we operate on the new structure. And if we have a g, we add our old stack to the garbage collector. All right. We need to create this stack copy function. So how do we copy a stack? We need to have a pointer. We need to assert that we have an S. And we need to have a new thing. So we'll have a for loop where we set P is equal to the S. We'll loop as long as we have a P next. And P will be equal to P next. But if we don't have a P next, then this stack is empty, or might also have a length of 1. Maybe we shouldn't do P next here, just P. And same here. And if our S is empty, we can just let's remove this garbage here, by the way, because I don't want to get into the occasion where we add it here and then here as well, and we have all different kinds of trouble. So the push and the pop functions will handle the garbage collector. Alright, so P is equal to S. But if we have an empty S, all we need to do is return make stack, because we will return a new empty stack. But if it's not empty, we want to loop. And what do we want to do at each iteration? So let's see. We need to create a new stack. So new is equal to make stack. And we'll need to have a see, what can we call that? Let's call it latest. It's not entirely accurate, but close enough. And we set latest to 0. We make a stack. And the new function should be equal to the old function. We want a memory copy into the new token. Do we have a copy function already for tokens? I don't remember. We have a T copy, but that's for a tokens pluralis. So I suppose we need to do this manually. So we memory copy into the new token. From the old token. But these aren't pointers, so I suppose we need to put the address like this. And size of struct s token. Alright, so that's for the token and the fun. What about the next and the previous? Well, the next we can't set quite yet. But the new previous should be equal to the latest. And then latest should be equal to this. But before we assign it to new, we should also do, if we have a latest, we should set the latest next to the current, like this. I think this is the right way to do stuff. And now we should have a copy of this linked list. So we return the new. But this new keeps changing. So we need to have a first, I suppose. Let's set first to 0 from the beginning. And if we don't have a first should be the new. and then we return the first. Okay, now I think it's right. So we make a copy. Last is find last. So the S prime previous should be equal to the last. No. After we have our coffee, we want to create a new one because we need a new entry. So P will be equal to an additional new stack. But only if S prime is equal to last. So if we are at the first entry, we don't need to create a new. We can just point P to S prime. Otherwise, we need to create a new. Now we can set P's previous to last. But if this is the first, previous should be empty. Maybe we should set last. No. Okay, we need an if statement here as well then. Or let's do it like this. So previous should be set to last, unless this is the first entry. In that case, previous should be empty. In both cases, next should be empty, because we haven't gotten that far. But if we have entries, we want to set the last next to P. And now we can populate this thing. So we can memory copy into p token from the t that we supply as a parameter to the function, and size of struct as token. And by the way, when we do this, we probably need to cast this to int 8. And then we have the function. So we probably need to create a function or a macro or something which matches a function from the HTML tag. So let's just for now say that pfun is equal to find function, and we give our t. And if we don't have function, if find function didn't find anything, we want to default to a function called id. And id should have the same signature as this, which we don't really know at this point, but well, we need to give a string as the argument as well. So we will have an ID. This is an identity function which basically takes the input and returns it. So it does nothing. So let's say we have a string s and a token which we don't need. So let's just do this. And let's code this function. Pretty simple thing. It will be a string ID. So we have a string s and a token nothing, and we return s. So let's temporarily define this find fun thing. So it will return a function. find fun. It will take a token T. And for the time being, no, that's not right. For the time being, we will just simply return zero. But this is temporarily. All right, I think it's starting to be time for testing this stuff. We can use what we have. Let's just create a token and let's set the token to x's, t's, and the first one. We probably want to do this. And let's create two. So we will have a stack old and a stack new. The old stack should be equal to an empty one, and the new should be equal to push operation of garbage and old and the token. And let's just print something from that thing. Let's take the address first. And if we have new, let's also print something from the token, perhaps. Let's print everything. So let's do one at a time. So we have token, fun, next, and previews. And for the token, we can do new token contents text token. Oh, let's do tag start, because this is a tag start. And then we have, is it data or starting to be a lot of different things. Hard to remember. So we have a tag star value, okay. Tag start value. So that's one. Token and fun. We can print the address of the function. So new fun. And then we have next and previous. Same there. New next. And new previous. Did I miss something? Yes. No. Oh, this is a wrong direction. Now it's better. Alright, I have no clue if this is going to work. Let's see what the compiler says. Okay, not that many errors actually. Conflicting types for scopy. Stack. Scopy. Stack star, scopy, stack star. Stack star, scopy, stack star. Why is that a conflicting type? Do I have another scopy perhaps? Yeah, that's probably it. Let's call this stack copy instead then. Okay. Union Anonymous has no member name tag start. Did you mean start? Yes, I did. Thank you, GCC. Oh. Unknown type token. 70. Passing over with one stack incompatible type. Right. We shouldn't pass the garbage collector any longer. In 97. That's right, because we're not really finished here, are we? We need to return P. Oh, I have a feeling that this will crash so badly. Huh. It didn't. It actually seems to work exactly as it should. But does it work if we push another thing to it? Because that is handled differently. So let's create something called middle or something. So the old is make stack. Then we have middle, which pushes the T. And then we have the new, which pushes middle and T plus 1, say. Then it crashes. We had to have a crash. Okay, so it works when the stack is empty. That's something, at least. So what are the specific things for a non-empty? We set S prime to stack copy. And we try to copy something of size 1. And what will happen then? We will have an S. It's not empty. How do we define empty, by the way? No function. So latest is 0, first is 0, P is S. Do we have a P? Yes. We create a new. If first is 0, which it is, first is new. New fun is P fun. We do a memory copy into new token. From P token of this size. We set the new previous to latest. And what is latest? Latest is 0 at this point. Shouldn't the latest be the current one? Let's see. We create a new thing. It might be the first thing. And if it's the first thing, previous should be 0, which it is. And then it's new. I think the stack copy succeeds actually. Let's see what's the last thing that happens. We malloc 4 times. Let's ask GDB. It's in the push. And we try to move something into memory from EBX. DS and this. Isn't this trying to move it into this address then, in memory? It's a weird address. C. Let's see. A is 10, B is 11, C is 12. What is this? Zero. This is just in the beginning of the function. No, it's not. It's just after the call to 0. but I don't see any call to 0. Maybe it's an optimization, inlining or whatever. Let's alter the make file slightly and remove all optimizations so it's a little bit easier to debug. Okay, now it looks different. Maybe we should do this instead. X30i EIP. Okay, so what's the next thing that happens? Some push operations and then memory copy. So it's before memory copy that we crash. That's useful information. Memory copy is here. P next is 0. Okay, this looks better. So here is a call to make stack. And then we just move around different registers. Make stack. So we are here or here perhaps. But probably here, because if we were inside of all of these if statements, we would see some jumps and stuff. And the only jump we have is this. And then it's the call to make stack. This jump is to 180. So no, that's not it. Make stack. We are here. P previous is equal to last. Is it possible? No. We should be able to set P previous. What about last next? Can find last return 0? Yes, it can if we don't have an S. But we do. But maybe we don't have an S prime. Can stack copy return 0? First is set to 0, and we return first. So is it possible that it still is 0? Maybe we can check the return value. If we break here, okay, so now we should see the return value instead of EX, right? Okay, it does return something. Okay, so it seems to return a stack. But it's all zeros. So we do a stack copy, we set last to find last. So what happens if we give the stack, the find last function an all zeros stack? We do have an S. So we set P is equal to S. Do we have a P? Yes. P is equal to P next, which is 0. And then we return that 0. Maybe we should do, if we have a P, we return a P, otherwise. we should probably return S, right? Okay, now it works. Easy peasy. Really nice. And if we print the next and previous of not new but middle, I don't like that the next is 0. Wait a second. P next is 0. And what is P? P is the new thing. But we shouldn't return P. That's the problem. We should return the first thing in the new list. So we need a first. And if it's empty, first is S. Otherwise it's still less. So we can just return S prime instead. We don't need a first. Hope this works. It's annoying. Everything seems to work perfectly, but we don't set the next, and I don't like that. We will return S prime, which should be the first in the list. Because we return the first here. The first is a new, but only if first is 0, so it should only set it to the first. What if we remove this? No. Last next is equal to P. Maybe we should have a case here anyway. So P previous. What happens if we do this? That's a bit unexpected. P is equal to S. I think the solution to this is we need to create a length function so we can make these cases a little bit better. Yeah, let's try that after this. Be right back. Did you know that I made a book about computer networking? You will learn how the internet works and how everything works under the hood. It's a complete beginner's course, but it has some advanced elements as well. And you will learn network design and network security and all different kinds of stuff. For more info, check out books.drbirch.com. That is books.drbirch.com. Thank you for your support. Sup guys, welcome back. I'm not really satisfied with the way I wrote these parser utility functions, so I'm going to rewrite a couple of those. But first I want to add to this structure, I want to have length. And I want to rewrite this, let's see, the make stack, giving it an argument. So we'll give it a length and we'll create a linked list of that length. So first we will create an empty structure and then we will fill it with data. I think that's a better way to do stuff. So let's see, those two we can keep. Let's move them to the top. And find last is a simple function, we can keep that. So then we have the make stack, the stack copy, the push. Let's comment these out for now. Maybe we'll use some of them or some parts of them, but for now let's just comment it out. So let's see, make stack, and we will have a size. No, wait a second. Let's keep this, but let's call it make entry instead. So stack make entry, and this will return. This will create a single entry of the linked list, while the make stack will create the entire list. So how do we write this new make stack? Well, as I mentioned, we need a size. And let's see, do we want it to be we would like to create an empty structure? Yes, I think we do. Or not a completely empty. It needs to be at least one. So let's do a for loop. And let's have a counter. We set n equal to the size. Loop as long as we have an n and we n minus minus. And at each iteration, make an entry. We need a last. And our new entries, previous, will be our last. And our new last will be this one. Before that, we set our last next to this one as well. And we need to save the first entry. So if we don't have a first, this would be our first. Then we return it. Simple enough. Let's also create a print function. I will not make this as involved as I did the show tokens stuff, because those we might use in our code. This will only be for debugging. So let's create a print stack. Let's wait a little bit with that, by the way. I want to create an index function. So it will return a stack. We'll give it a stack and an index. So we can index into like the first entry, the second entry, and so forth. So stack index. We will have an S and an index. Maybe we should name the function index like this. By the way, we need to set the length of this thing. So the first, and the length will only be at the first linked list. So first length is size. I don't think I want an int 16, by the way. I want a signed short int. Because I want to be able to index into -1 as well, which will be the last one then. So signed short int. We need to assert that we have an S. Let's do separate. We assert that we have an S. We assert that the length is greater than the index. And if the index is less than 0, we want to do one thing, otherwise we want to do something else. So let's start with something else. We'll have a for loop where we set n equal to 0, or no, n is equal to the index. And as long as we have an n, and in this case the index is positive, maybe we should go the other direction. So let n be 0. And as long as n is less than the index, we'll increase it. We will also set our pointer to be equal to the first stack. At each iteration, this should be equal to next. Maybe this is all we need. And if the index is less than 0, we want to set n equal to 0. We want to set p equal to not s, but find last s. And we want loop as long as n is more than the index. We'll do n minus minus, and we'll do p is equal to p previous, so we go backwards. So if we have -1, n is 0 and index is -1, so n is more than index. It will return the last one, yes? And if, no, we don't need an if, I think. We should just be able to return p in this case. Okay, so that's an index function. Now it should be pretty simple to create our stack copy. And I think I do want to have the garbage collector here. So let's assert that we have a G. No, we don't need to assert that. But we need to assert that we have an S and that we have a length. In that case, we can create a new stack of size length. And now we just need to go through that and copy everything. So let's double check that we have one of those. If we don't, we return an error. And now we just need to go through the brand new stack structure and go through the old one and just copy from new to old. So let's have a new pointer and an old pointer. We'll make a for loop. We set n equal to 0. We want to loop as long as n is less than the length. We want to set the new pointer equal to the new and the old pointer equal to the old. At each iteration, we want the new pointer to be equal to the new next and the old pointer to be equal to the old next. And then we can do something like copy entry. We copy into the new from the old. And one more thing. At each iteration, I want to add, if we have a garbage collector, I want to add to the garbage collector the old thing. And what is this copy entry thing? Well, let's define it as a macro. So copy entry destination source. And we want do. So what do we have inside of these? We have a token, a function, and at the first location we have a length. So let's start by setting the new length. No, we don't need to do that because we do that in our make stack, don't we? Yes. So all we need to do is first of all copy the token. So memory copy to the address of destination from the address of source, size of, no wait, it should be destination token, source token, and size of struct s token. And let's also set the destination function equal to the source. The source function. Okay, I think this is going to work. Let's put it into our H. And when we have added, copied everything, we should just be able to return the new thing. And let's go back to this print function. So void print stack. We need a stack. And we need a pointer. We need an n. So we set n to 0, p equal to s. We loop as long as n is less than s length. at each iteration n plus plus, and p is equal to p next. And then we print a bunch of stuff. Something like this. It will be pretty similar, but I will only do one printf for everything. Something like this. And what do we have? We need to have the P and the P token contents. Let's do text token like we did before. Value. And then we have the P next and P previous. Like so. And then we return. So that's our print stack function. And we have index, find last, stack copy. Yeah, I think we can create our push function now. And it should be fairly straightforward, I hope, with all these additions. So we'll create our push. We'll take a garbage collector. We'll take a stack and a token. We assert that we have a stack and a token type and a stack length. So first we make a copy of this thing. Maybe we should name them. Yeah, let's call this S prime so we know it's a new thing. S prime will be equal to stack copy garbage S. If we don't have an S prime, we'll return error. So when we have this new copy, we want to create a new blank entry. And we want to set let's create the last as well. So last will be the index of our new stack -1. And our last next is our new thing, the entry. And our entries previous is the last one. And our new stack will have a greater length. And then we'll just do a memory copy. Or let's do a copy entry. The destination is our new entry. And the old, well, we don't have an old for this, do we? No, we need to do this manually. So we memory copy into our entries token from our T, size of struct as token, and then the function. And the function would be, let's see, entry fun is equal to find function T. And if we have a G, we can run the garbage collector. We don't need to care about the return value. Or do we now? Possibly. So let's do this. And we want to return our S prime. Okay, this function was a little bit easier to write than the last one. Will it work better though? So let's see, what do we have here? We create a new stack of size 1. And we set the function equal to find function based on our t. Let's wait with this middle thing. Let's do a memory copy into our token from our, let's see, from our T, like this, I suppose. No. Or yes, I think that's right. Size of struct as token. So now we have one thing. Then we call new, and we push onto our other token. Then we can print our stack, new stack. We can run our GC, not caring about the return value, and return. All right, let's see how this will be after we have cleaned it for errors. Conflicting type index with stack sign short int. Stack sign short int. Maybe it is. Maybe there is already a function index. Yes, there is a deprecated function index. How can we make our index take precedence? Maybe we can. What if we make it static? Will that make a difference? Nope. It's included from string.h. Do we really need that thing? I don't think we do. Let's remove this. Middle is an unused variable. I don't care. Warning: index declared static but never defined. Static stack index. Static stack index. Why does it say that? Oh, it's when it's inside of the hyperbird. We need, but we are including the parser.h. Ah, wait a second. We don't have access to the static things, of course. Let's do this the old-fashioned way. S is a pointer. Oh, I forgot the 4. Up is a pointer. Oh, what's this now? Unknown type name string parser.c. So where do we have this? Well, we need to include hyperbird.h. probably the rest as well. Let's take one at a time. Huh, it compiled, but will it work? No, segmentation fault. But I'm not really surprised. Okay, we zero out some big thing. Let's see where we're at in GDB. Make stack is crashing. So we're trying to move into memory the contents of EDX. What do we have there? Something which is empty, but more interestingly, what do we have inside of EX? A 0. So let's see. Make stack. Last is 0, first is 0. N is equal to size as long as we have an n minus minus. We make an entry. If we don't have a first, this will be our first. Our previous will be last, which is 0 from the beginning. And if it is 0, we can't do this. So let's double check that we have a last, and then we do this. Let's see what happens this time. Still seg faults, but perhaps at a different location. Yes, now it's in the print stack. Similar error though. So we have a 0. And it's right before the print F. So n is 0, p is equal to s. We'll loop as long as n is less than the length. We'll increase n, and p will be equal to p next. I wonder if it's this thing. P token contents text token value, because we might not have a token. So let's check that we have a p token type. Then we do this, otherwise 0. Maybe it's just type. Okay. So let's see where it segfaults this time. Still in print stack. At the same location. So that's not a problem. Well, this should be a string. Maybe this is a better option. But I'm not sure it's that this is the problem. Let's assert that we have an S and an S length. Oh. Pointer type mismatch. Expression has int 8, right? We need to do this. Alright, so this assertion fails. Let's split it up into 2 lines. So we check both that we have an S and that we have a length. We don't have an S. Interesting. So if we have new, we'll do this. Otherwise, push failed. Okay, so why does push return a 0? Or more interestingly, what can make push return a 0? Well, if stack copy fails, we return a 0. If we don't have a last, so if this index fails, we return a 0. Let's just add a temporary thing here so we know what we're dealing with. If we don't have an S, like so. And I don't put it inside of this because I want to be able to delete it easier. Okay, so this is not the place. Alright, so our index function fails when we give it a -1. So if index is less than 0, which it is, we set n to 0, p to find last, as long as n is more than the index. So first it's 0, which is more than -1. And then it will be 1 less, which is -1. And -1 is not more than -1. So we should do one iteration. And p is equal to the previous. Maybe we could do something like if s length is equal to 1, we early return s. Okay, look at this. Isn't it beautiful? So we have a stack of size 2 with an entry at this location. We have an HTML. Next is pointing to this address, which is this entry. Preview is 0. And this first one is an HTML, the second one is body. Next is 0. Previous is this 2500, which is this entry. It works perfectly. Let's remove those, this warning thing. Wait a second, it works, but it's segfaults. Is it our garbage collector that segfaults? Yes. And I think I know what it is. inside of our push, let's not run the garbage collector. Let's do that manually at the calling site instead. Like here. Okay, now it works perfectly. Alright, so now we are successfully able to build a stack of HTML entries. So now we just need to start parsing. And that's our next logical step. If you liked this episode, please like and subscribe. And thanks for watching. Thanks for today.